Hi everyone. Today we're going to study logarithmic functions. Let us define logarithmic function. For b greater than 1, the b is the base, and b is not equal to 0, the inverse of f of x equals b raised to x. This function is an exponential function denoted by f inverse of x equals log of x base b is the logarithmic function with base b. The general form of logarithmic function is f of x equals log of x to base b. So in here, the inverse of the exponential function is the logarithmic function and vice versa. We read this notation as log of x to base b. Please note that x equals b raised to y is equivalent to y equals log of x to base b. This is the exponential form, and this is the logarithmic form. As an example, if we have 3 square equals 9, this is equivalent to log of 9 to base 3 equals 2. Take note, the number 3 here is the base of the exponent, and in the logarithm, the number 3 is also the base. The number 2 is the exponent, and that is the logarithm value of the logarithmic form. And this number 9 is the same number for the logarithm. Here is a quick look of the graphs of logarithmic function. This is the graph of y equals log of x to base b, where b is between 0 and 1. While this is the graph of y equals log of x to base b, when b is greater than 1. Let us proceed with properties of logarithmic functions. If b, capital M, capital N are positive real numbers and b is not equal to 0, and p and x are real numbers, then we have here the first 4 properties of logarithmic functions. Number 1, log of 1 to base b equals 0. Property number 2, log of b to base b equals 1. Number 3, log of this b raised to x to base b equals x. And this x is simply that exponent of the b. Property number 4, when we have a number b raised to log of x to the base b, this is equal to x, and this x is the number of the log. There is a condition that x is greater than 0. It means x must be positive. Let's have the 5th, 6th, 7th, and 8th properties of the logarithmic functions. Let's have number 5. The log of m to base b equals the log of n to base b if and only if capital M is equal to n. This property is used normally when we are solving equations. Property number 6. This is the log of a product mn. If we're going to take the log of the product mn to base b, this is equal to the log of m to base b plus the log of n to base b. Property number 7. This is the log of a quotient. When we have m over n, and we will take the log of that to base b, this is equal to the log of capital M to base b minus the log of n to base b. Property number 8. The log of this m raised to an exponent p to base b, this is equal to the p, which is the exponent, is now put down as a factor. So this is p times the log of m to base b. Take note of this property 6, 7, 8, because the logarithm lightens up the respective operations. Look at the product. This is equal to the sum of each factor. For number 7, the division becomes subtraction. And for number 8, the exponent or the power becomes product in here. There are types of logarithmic functions and relationships. The first is the general logarithm, where we see y equals log of x to base b. The condition is b must be greater than 0, or we say b is positive, and b is not equal to 1. Also, x must be greater than 1. The next type is common logarithm, and this is equal to y equals log of x to base 10. We say that this is common logarithm when we have a base of 10. And if we have a base of 10, we can simplify the log notation into log x. So in here, the base is not written. So every time we see a log without any base, that is understood to be base 10. And we call this common logarithm. The next type is natural logarithm, and this is y equals log of x to base e. And we can simplify the notation by writing ln of x. This ln of x means it is a logarithm with base e. There is a relationship about log of x to base b. We can simplify this by taking the quotient of log of x to base 10 over log of b to base 10, or we can write ln of x over ln of b. Take note, the log of the x will be in the numerator, and the base, which is the b, will come as the log of b in the denominator. Let's go now to examples. This is example 1. Change each logarithmic form to an equivalent exponential form. We have here our conversion formula. So letter A is log of 5 to base 25 equals 1/2, and letter B, log of 1000 to base 10 equals 3. So let's start with letter A. This is the equivalent exponential form. Take note, this is log of 5, so we will write here the number 5 equals, the base is 25, so we will use this base as the base of the exponent. And this 1/2 here is exactly the exponent. So we have 5 equals 25 raised to 1/2. So this is the answer for letter A. For letter B, the equivalent exponential form is 1000 equals 10 raised to 3. From the given problem, log of 1000, we're going to write this 1000 again here, and this is equal to the base 10 of the log is the same base for the exponent, and this number 3 is the exponent in here. So 1000 equals 10 raised to 3. This is our final answer. Let us have the reverse process. Change each exponential form to an equivalent logarithmic form. Again, let us write our conversion formula. And we have two problems here, A and B. This is 36 equals 6 squared. And letter B, 7 equals square root of 49. Let's begin with letter A. And this is equivalent to 2 equals log of 36 to base 6. Now, this number 2 is the exponent of our exponential form. And we write equals. We put the log of the number 36, we copy here. And the base 6 of the exponent is the same base of the logarithm. So this is our answer for letter A. Now for letter B, 7 equals the square root of 49. Let us convert the square root of 49 into rational exponent. So we have 7 equals 49 raised to 1/2. And from here, we will now write the equivalent logarithmic form. This is the equivalent logarithmic form. The 1/2 or the exponent in here will be our answer here, 1/2, then equals. We will write the log of the number 7, we will write here, and this base 49 of the exponent is the same base for the logarithm. So our final answer is 1/2 equals log of 7 to base 49. This is our final answer. Let's have example 3. Find x, b, and y as indicated. So we have here 3 problems, A, B, C. Letter A is log of 16 to base b equals 2. Letter B, log of 64 to base 8 equals y. Letter C, log of x to base 2 equals 3. First, let us write our conversion formula here. Our main goal now is to convert each of these problems into equivalent exponential form and solve using exponential property. Let's begin with letter A. The equivalent exponential form of letter A is b squared equals 16. The b is the base, so I write the base here, and this number 2 is the exponent, so we have b squared. And this is equal to this number 16. Now, I know that this 16 is the square of 4. So I can show that b squared equals 4 square. And then I'm going to use a property of exponential function. I remember there is property number 3 that says a raised to x equals b raised to x if and only if a equals b. I can see here that the exponents are the same. So it means I can simply copy the b down here equals 4. So I have here b equals 4, and this is my answer for letter B. It means the value of b equals 4. I will just copy this answer opposite letter A. I will go now to letter B. I will convert this into equivalent exponential form. And this is the exponential form. 8 raised to y equals 64. Again, we see the base here, the log with base 8. I copy that same base in here. And this y is the exponent that I can use here. So 8 raised to y. And this is equal to, this number 64 is now here. And I know this 64 is equal to 8 square. So I have now 8 raised to y equals 8 square. In this portion, I can see that I have same base for the left and the right sides of the equation respectively. So I remember property number 2 of exponential function, and that is a raised to x equals a raised to y if and only if x equals y. I can see that I have same base, so it means I can copy the exponents of the left side, which is y, and this is equal to the exponent of the right side, which is 2. So I have now this equation, y equals 2. And this is the value of y that I want to derive from problem B. So I'll just copy this answer opposite letter B. The y equals 2. I will go now to problem C. The log of x to base 2 equals 3, and I will find the x. I will now write the equivalent exponential form of letter C, and that is 2 cubed equals x. Again, the log with base 2, I will copy that number 2 here as the base also of the exponent. The number 3 is the exponent itself. So that is 2 raised to 3. And this is equal to this number x. And I will copy it here. I will just simplify the 2 cubed, and this will give me 8. So 8 equals x. And this equation gives me the value that I want, that x equals 8. This is my answer. I will just copy this opposite letter C. So we are now complete with our answers for A, B, and C. Today, we're going to study characteristics of the graph of the function f of x equals log of x to the base b. In some books, you will see the topic about characteristics of the graph of the parent function f of x equals log of x to the base b. This is the graph of this function when b is greater than 1. While this is the graph of the function when b is between 0 and 1. For any positive real number x and constant b greater than 0. Of course, b is not equal to 1. See the following characteristics in the graph of f of x equals log of x to the base b. First, it is a bijective function. It means it satisfies one-to-one function and onto function. The vertical asymptote is x equals 0, or we say that the y-axis is that vertical asymptote. The domain is from 0 to positive infinity. The range from negative infinity to positive infinity. The x-intercept is 1, 0. And there is a key point, that is b, 1. Remember that this b is the base of the logarithm. The y-intercept is none. We say that the graph is increasing if b is greater than 1, and this is the graph, while decreasing if b is between 0 and 1. This is the graph. Today, we're going to study graphing logarithmic function of the form f of x equals log of x to base b. Here are the 5 general steps. Step 1. Draw and label the vertical asymptote, that is x equals 0. The vertical asymptote is the y-axis itself. Step 2. Plot the x-intercept, and that is the point 1, 0. Step 3. Plot the key point, and that is the point b, 1. Note that this b here is the base of the logarithm. Step 4. Draw a smooth curve through the points. Step 5. State the domain, that is from 0 to positive infinity. The range, that is from negative infinity to positive infinity. And the vertical asymptote, that is the x equals 0. Let's see this example. Graph f of x equals log of x to base 5. State the domain, range, and asymptote. Let us first identify the behavior and key points for the graph. Since b equals 5 is greater than 1, the function is increasing. It means the left tail of the graph will approach the vertical asymptote, which is x equals 0, and the right tail will increase slowly without bound. The x-intercept is that point 1, 0. And we have the key point 5, 1 that is on the graph. Again, this 5 here comes from the base of the logarithm. We draw and label the asymptote, plot and label the points, and draw a smooth curve through the points. This is now our graph in blue. This is the graph of f of x equals log of x to base 5. This is our vertical asymptote, which is the y-axis itself. The x-intercept is here, the point 1, 0. And the key point is the 5, 1. These 2 points are on the graph. Now for the domain, we write from 0 to positive infinity. The range from negative infinity to positive infinity. And the asymptote, which is the line x equals 0 or the y-axis itself. This is the final answer. Today, we're going to study horizontal shifts of the function y equals log of x to the base b. In some books, you will see the title Horizontal Shifts of the Parent Function y equals log of x to base b. For any constant c, the function f of x equals log of the function x plus c to base b shifts the parent function y equals log of x to base b to the left c units. If c is greater than 0, it means c is positive. Or shifts the parent function y equals log of x to base b to the right c units if c is less than 0, or we say that c is negative. It has now the vertical asymptote x equals negative c. And the domain will be from negative c, comma, to positive infinity. The range is from negative infinity to positive infinity. Let us see now the graph of g of x equals log of the function x plus c to the base b. Here we have two graphs. This graph in blue is the graph of the parent function f of x equals log of x to base b, while this graph in red is the graph of this g of x equals log of x plus c to base b. Please note that the x-intercept has the coordinates 1 minus c, comma, 0. And the key point, now the asymptote changes to x equals negative c. This broken line here is the asymptote. The domain changes to negative c, comma, positive infinity, while the range remains from negative infinity to positive infinity. Here now is the graph of h of x equals log of x minus c to base b. You can see here two graphs also. This graph in blue is the graph of the parent function f of x equals log of x to base b. This graph in red is the graph of h of x equals log of x minus c to base b. Take note that the x-intercept of this new function has coordinates 1 plus c, comma, 0. And the key point has coordinates b plus c, comma, 1. Note that the asymptote changes to x equals c. Here is the asymptote, the broken line here. The domain changes to from c, comma, positive infinity, while the range remains from negative infinity to positive infinity. Today, we're going to study vertical shifts of the logarithmic function y equals log of x to base b. In some books, you will see this topic that says vertical shifts of the parent function y equals log of x to base b. For any constant d, the function f of x equals log of x to base b plus d. Shifts the parent function y equals log of x to base b going up d units if d is greater than 0, or we say that d is positive. Or shifts the parent function y equals log of x to base b going down d units if d is less than 0, or we say that d is negative. The vertical asymptote is x equals 0, or we say that the y-axis itself is the vertical asymptote. The domain has the interval from 0 to positive infinity. The range is from negative infinity to positive infinity. Let us analyze now this shift up function, the g of x. This is equal to log of x to base b plus d. Here we see two graphs. This graph in blue is the graph of the parent function f of x equals log of x to base b, while this graph in red is the graph of g of x equals log of x to base b plus d. Take note of two important points for the g of x. The first is the x-intercept with coordinates b raised to negative d, comma, 0. Another key point is b raised to 1 minus d, then comma, 1. The asymptote remains x equals 0, or the y-axis itself. The domain remains from 0 to positive infinity. The range remains from negative infinity to positive infinity. Now we have a shift down function h of x equals log of x to base b minus d. We have here two graphs also. This graph in blue is the graph of the parent function f of x equals log of x to base b. Now, this graph in red is the graph of h of x equals log of x to base b minus d. Take note of the two important points of the h of x. The first is the x-intercept with coordinates b raised to d, comma, 0. Another key point here is b raised to 1 plus d, then comma, 1. The asymptote remains x equals 0, or the y-axis. The domain remains to 0, comma, positive infinity, while the range remains from negative infinity to positive infinity. Let us see this example. Sketch a graph of f of x equals log of x to base 3 minus 2 alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. First, let us note that in the problem, the value of d is negative 2. Or we say that d is less than 0. So this means we will shift the parent function f of x equals log of x to base 3 going down 2 units. We note that the vertical asymptote is the y-axis itself, that is x equals 0. Here are now our graphs. The graph in blue is the graph of the parent function y equals log of x to base 3, while this graph in red is the graph of f of x equals log of x to base 3 minus 2. Let us consider the three key points from the parent function, namely 1 over 3, comma, negative 1. This is the point. Another point is 1, 0, or the x-intercept itself. This is the point. And the other point is 3, 1. This is the point. The new coordinates are found by subtracting 2 from the y coordinates. So for the point 1 over 3, comma, negative 1, it becomes 1 over 3, comma, negative 3. This is that point. For the point 1, 0, we have now 1, comma, negative 2. This is the point. For the point 3, comma, 1, it becomes 3, comma, negative 1. This is the point. The three new points are the points for the shifted function. Now, the domain is from 0 to positive infinity. The range is from negative infinity to positive infinity. And the vertical asymptote is the y-axis itself. And our equation, x equals 0. This is now the final answer. Today, we're going to study reflections of logarithmic function y equals log of x to base b. In some books, you will see this topic, reflections of the parent function y equals log of x to base b. The function f of x equals negative log of x to base b reflects the parent function y equals log of x to base b about the x-axis. Let's see one example. G of x equals negative log of x to base b. Here is the illustration. We have two graphs here. This graph in blue is the graph of the parent function, while this graph in red is the graph of this g of x equals negative of log of x to base b. The reflected function or this g of x is decreasing as x moves from 0 to infinity. The asymptote remains x equals 0 or the y-axis. The x-intercept remains the point 1, 0. The key point changes to the point b raised to negative 1, comma, 1. The domain remains from 0 to positive infinity.
The range remains from negative infinity to positive infinity. Now, the function f of x equals log of negative x to base b reflects the parent function y equals log of x to base b about the y-axis. Here we have one example. H of x equals log of negative x to base b. Here is the illustration. This graph in blue is the graph of the parent function f of x, while this graph in red is the graph of the reflected function h of x equals log of negative x to base b. The reflected function is decreasing as x moves from infinity to 0. The asymptote remains the x equals 0 or the y-axis. The x-intercept now negative 1, 0. The key point changes to negative b, 1. The domain changes to negative infinity, 0. The range from negative infinity to positive infinity. Let us see this example. Sketch a graph of f of x equals log of negative x alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Let us identify the behavior and key points for the graph. We can see here that our problem is a common logarithm. Since the base equals 10, which is greater than 1, the parent function is increasing. Since the input value is multiplied by negative 1, f is a reflection of the parent graph about the y-axis. Thus, f of x equals log of negative x will be decreasing as x moves from negative infinity to 0, and the right tail of the graph will approach the vertical asymptote x equals 0. The x-intercept is the point negative 1, 0. Let us now draw and label the asymptote, plot and label the points, and draw a smooth curve through the points. Here are now the graphs. This graph in blue is the graph of the parent function, while this graph in red is the graph of f of x equals log of negative x. The x-intercept is here, the point negative 1, 0. And there is this one key point, which is negative 10, 1. For the domain, we write from negative infinity to 0. The range is now from negative infinity to positive infinity. And the vertical asymptote is the y-axis, and we write x equals 0. This is now the final answer. Today we're going to study natural and common
logarithmic functions. First, let us define natural logarithmic functions. The function f of x equals ln x is the natural logarithmic function with base e. Thus, the log of x with base e equals ln x, where x is greater than 0. It means x must be positive. This f of x equals ln x can be written as y equals ln x. And this function is equivalent to the exponential expression x equals e raised to y. Next, let us define common logarithmic functions. The function f of x equals log x is the common logarithmic function with base 10. Thus, log x to base 10 equals log x, where x is greater than 0. It means x must be positive. There is a note: when the base of the logarithm function is 10, we call it the common logarithmic function, and the base is not shown. Likewise, if the base of a logarithm is not shown, we assume it as 10. The f of x equals log x can be written as y equals log x. And this expression is equivalent to the exponential form x equals 10 raised to y. Let's have this example 1. Rewrite in exponential form and find x to 3 decimal places. Letter A, log x equals 3. Letter B, ln x equals 2. Let's begin with letter A. Take note that the log x equals y is equivalent to x equals 10 raised to y. It means to say this log x equals 3 is equivalent to x equals 10 cubed. Simplifying this 10 cubed will give x equals 1000. And this is the value that is required for problem A. We will copy this opposite problem A. Here we go. Now, let us answer problem B. ln x equals 2. We know that ln x equals y is equivalent to x equals e raised to y. Thus, the ln x equals 2 is equivalent to x equals e square. And this e square, using calculator, we will get the value x equals 7.389. And this is the required value for x. We will copy this opposite problem B. Here we go. So we are done with our example 1. These are the final answers. Let us have example 2. And this is solving logarithm inequality. So the problem is to solve for x. The inequality is the log of the quantity x minus 1, then plus the constant 2 is less than the log of the quantity 2x minus 5, and then plus the constant 2. For our solution, let us copy again this inequality down here. And the next step is to subtract positive 2 to both sides of the inequality. We can see that both sides have the constant 2. So if we subtract 2 to both sides, the constant 2 here will be cancelled out. And then let us copy the remaining logarithms on the next line. The next is, we will put all logarithms in one side of the inequality. Let's say we will put this right side logarithm to the left side. So what we will do is to subtract the log of the quantity 2x minus 5 to both sides. So here we go. The log of 2x minus 5 is subtracted to the left side and to the right side. Look at our right side. We have the same quantity being subtracted, so we will cancel out the right side and this becomes 0. Next is, let us simplify our left side where we have two logarithms. Let us remember that the log of a quotient a over b equals log of a minus log of b. In the same way, we can interchange this idea that log a minus log b is equal to the log of the quotient a over b. So simplifying our left side of the inequality, we can simplify the expression here into log of the quotient x minus 1, that is the numerator, over the denominator 2x minus 5. And this is less than 0. To simplify this line here, let us remember that log x equals y is equivalent to x equals 10 raised to y. To extend this idea, we may write also that the log of x less than y is equivalent to x is less than 10 raised to y. It means to say, this expression here can be simplified further into x minus 1 over 2x minus 5 is less than 10 raised to 0. If we simplify the 10 raised to 0, we will get 1. And from here, we're going to solve for x. Let us cross multiply the denominator to our constant on the right side of the inequality. So 2x minus 5 times 1. Let us continue on this side. So we will have x minus 1 is less than 2x minus 5. Now let us solve for x, putting all variables on the left side and all constants on the right. So this 2x here, we will transpose on the left side. From positive, it becomes negative. And this negative 1, we will transpose also on the right side. From negative 1, it becomes positive 1. So we have now here x minus 2x is less than negative 5 plus 1. Simplifying our inequality here, on the left side, x minus 2x will give negative x is less than, the negative 5 plus 1 is negative 4. Let us multiply this inequality by negative 1, and the rule says multiplying by negative number makes the inequality sign reversed. So the inequality times negative 1, this negative x times negative 1 will give positive x, and this less than sign becomes greater than, and then negative 1 times negative 4 will give positive 4. So we have our answer, x is greater than 4. This is our final answer. I hope you learned something from this video. See you again next time.